So good morning, everyone. The topic of today's discussion is going to be careers in data sciences, becoming a better data scientist. Okay, so that's going to be the topic of today's discussion. And I'm sharing my screen, so in case you have any trouble sharing, let me know. Okay, so just give me 1 minute. Yeah. So you should be able to see my screen, and this is the agenda for discussion today. So the plan, like Aaron mentioned to you, is for me to present for an hour or so and then open up for questions. Of course, if you have any questions in the interim, you have a chat window where you can actually put in your question, and I may pick the question periodically and answer it. Okay. So the agenda for today is I'll talk about my career journey in data sciences, which will be followed by the career learnings I've had from a data sciences perspective, like what is my view on data sciences. What are some careers in a lot of you will have careers in B2C, some of you will have careers in B2B. What are some paradigm differences between careers in B2B and B2C? Then to have a successful career in data sciences, you can either be a data scientist or you can be like a data scientist manager. So what are some elements of success for a successful data scientist and for a successful data scientist manager? Then how you can innovate as a data scientist, both in external forums outside your organization and internal forums, which is within your company. Then a lot of people always ask me, like, what you can do to build better models, how can you win a data science competition. So the last section will be about last mile optimization, which is like how to get that top 5% or 3% or maybe even better the top 1% in accuracy, so that we're confident that the model that we build is within the top 3 or 5 models that can be built for that particular problem. So what to do to build better models. Then I will go through a case study of winning a data science competition, which is the KDD Cup, which is the most prestigious competition. So, and then we'll follow it up with Q&A. Okay. Aaron, you're able to hear me, right? Yeah.
Yes, sir, we can.
Yeah, cool. So this is about my career journey in data sciences. So I have played multiple IC and people manager roles. I started out with Dell as an analyst in analytics, then grew to be an advisor, a consultant, a manager, and I was managing. In my last role, I was a senior manager there. Moved on to Amazon. I headed up marketing, headed up affiliate analytics there. Then went to Flipkart, where I headed marketing and customer analytics. And my current role, I lead data sciences and advanced analytics, for VMware in India, and I also represent Dotted Line, the Enterprise Information Management Organization. Some of the things on data sciences, apart from work, have also been a top player on Kaggle for a year in 2013-14, where I was ranked in the top 10. I'm a Kaggle Grandmaster, have won the KDD Cup. I also have run a freelancing setup for US startups, where I worked on multiple interesting problems like imputation of genomic data to predicting the prices of packaged milk futures on the US exchange. On the professional side, there have been a couple of case studies we published with Harvard. Filed a few patents. So what I'll do is, this is my career journey in data sciences so far, telling you like what I've done in the past. And next I will talk about like what are my perspectives on data sciences, how I see data sciences in B2B and B2C as different, and about careers in data sciences. Okay. See, data sciences has got many definitions, definitions, and everything is very semantic. It's more like analytics. So if you talk about analytics to different people, everybody will say I'm doing analytics in some form. For somebody, adding two numbers is analytics. For somebody, doing a chart in Excel is analytics. For somebody, doing a propensity model is analytics. It means different things to different people. So there is, whenever we come up with definitions, we have to remember that the definitions are all very semantic in nature. So the definition for me may not be the definition for somebody else. So you look up definitions in data sciences, you're going to get like a lot of definitions worldwide on when you search on Google or something like that. What is my definition of data sciences? I say data sciences is exploiting data to handle uncertainty. When there is certainty, there is no data science. So if I ask you a question, what is the sales of your organization? I was going through the attendee list. I see many people from Walmart. I see many people from Infosys, Wipro, Mindtree, and Mercedes-Benz, and all of these places, right? So if I ask you a question, what is the sales of your company in the last year? there's no uncertainty in it. There's only one right answer for it, and it will be like select sum of revenue a year from table group by year will tell you like the sales by the year. So these are all business intelligence problems. Now, if I turn the problem on its head and say, hey, what is the revenue of your company going to be in the coming year? Then there is uncertainty. You can come up with an estimate, but you cannot come up with the point estimate because the point estimate is likely to be wrong. You can come up with an interval estimate to say, hey, you know what, the revenues of my company are going to be between like maybe 4 billion and 4.5 billion. And I think it'll be somewhere over there, right? With some some percent of confidence. So that is the problem of uncertainty. So data sciences is exploring data to handle uncertainty. Where there is no uncertainty, there is no data sciences. Okay. So data sciences, the funny part about data sciences is it's not only that the problem is uncertain, the output is also uncertain. So if we have a problem in a financial services company to say who is likely to default, the problem is that we can say that these 200 people are most likely to default, but we cannot be certain that the 200 people are going to be default. No? So there is uncertainty both in the problem as well as in the outcome, which is what makes data sciences so exciting. And the idea is that even though the outcome is uncertain, if I say that 200 people are going to default, and actually if 50 people default, they should be captured on the top of they should be captured within my 200. No, then I'm useful to the business. So data science is the art of exploiting data to handle uncertainty. Where there is certainty, there is no data science. And what are the types of uncertainty that data sciences can handle? There are three types of uncertainty it can handle. One is to predict a numeric outcome. For example, how many customers will Flipkart have in the coming year? Okay, or how many mobile phones will I sell at Flipkart in the coming year? So that is a numeric outcome. And the vast majority, or I can take even simple example, what is going to be the salary of people who graduated from let's say a particular college in the next year, right? So these are all problems of uncertainty, but the target variable, what we're trying to predict, is numeric in nature. So it could be like, in the business world, it could be bookings or revenue or number of customers or partner rebates, anything. Now, the most common problem in data science is always classification. Prediction problems are not as common. Classification is when you try to group people into buckets. Like, you can group customers into buyers and non-buyers. You can classify orders into likely to close in the quarter, not likely to close in the quarter. You can classify a bank customers as likely to default and not likely to default. You can do a prediction. Is it going to rain? Is it not going to rain? So in a classification problem, the target variable is categorical or or binary, like the 0, 1 kind of thing, or it could be like multiple classes as well. In a numeric outcome, you're trying to predict something which is an interval variable, like sales or bookings or number of customers. When you try to predict a number, it is numeric. It's a prediction problem. When you try to group people into buckets like defaulter, non-defaulter, it's a classification problem. The third type of problem is actually, segmentation, where you don't have a target. So if you try to segment all customers that are coming to Amazon.com, you're not really having a target segments in mind, right? You're looking at their similarity, coming up with some distance measures, and then saying, how similar they are. For example, I may be similar to another person because both of us wear a watch and both of us wear spectacles, and we may be different that we are wearing jeans and formal pants. In which case, the distance between us, using a very simplistic measure, could be that out of 3 attributes, 2 are similar. So segmentation is a case of unsupervised learning because there is no target variable. You're just trying to group people based on the similarity between them. So that is unsupervised. When you have a target variable and you're trying to learn a function that determines how the target variable is a function of the other variables, it is supervised learning. So, to summarize, data science is the study of uncertainty. There are three types of problems. One is predicting a numeric outcome like sales or bookings or number of customers. Second is a classification problem, which is grouping people into buyer, non-buyer, or defaulter, non-defaulter. Third is segmentation. When we have a target in mind that we're trying to predict or classify, there is a supervised learning, which is the first 2 examples, and the third is unsupervised. So data sciences is a very interdisciplinary field. Like, it requires a strong amount of computer science and mathematics knowledge. So when I say computer science, it's like, you need to be good at programming. If you don't program, you can't be a data scientist. Okay, and you can't be effective manager of data sciences as well unless you understand the nuances of some of these things. So it includes computer science, it includes mathematics, it includes statistics, and it includes business. Okay, and when I say statistics, see, a lot of us have studied statistics in college, and in statistics we hear about all these values like p values and confidence and all of these things. If you look at all the modern packages like R or Python, they don't even output p values. So just wanted to share my perspective on that. Statistics is a study of trying to say, is my sample representative of the population? In the olden days, the data would be very limited. They would enter the data in books, and the number of records would be in few hundreds. So the statistician's problem was, for example, if I collect the height of all the people who have attended this webinar, can I say that the height of the people in India is the same as the average height of the people that attended this webinar? Now, it could be, it could not be. And the sample, one way to argue is the sample consists of people interested in data sciences, so it is a very biased sample. So maybe it will tell us the average height of the people who are interested in data science. So can we make that assumption? So statistics, what statistics does is, if you take any statistical package, it outputs p-values, it outputs confidence, and it says basically something called standard error. So standard error means if I have a sample of the 1,000 odd people in this webinar, and then if I take different samples of it, like I take 100 people, I measure their average height. I take the next 100, I measure average height. I take randomly 100 many times. Then if I take the standard deviation of the samples, is a standard error. Now, like in electronics, there's something called a signal to noise ratio. So suppose we find that the standard deviation of the samples when I draw from the population is when the standard deviation of the subsamples I draw from a sample is very low, I can have a high confidence in my result, and the p-value will be low. Now, there is a traditional statistical approach where you have limited data and you try to infer the population. The reason why the modern packages like R, Python, they don't output p-values is they work on the concept of machine learning, which is saying, hey, I've got a large data set with me. Can I actually repeat my algorithm many times where I run it on like 4 buckets, test it on the 5th bucket, and repeat the process several times? So data sciences and all the techniques that we learn today are a paradigm shift from the traditional statistical world. So to summarize, data sciences handles uncertainty, 3 types of problems: numeric, outcome, which is prediction; categorical or grouping, which is classification; and segmentation, which is unsupervised. And it is an interdisciplinary field, and there is a difference from the traditional statistical world. Most of the problems in data science is a classification. So the steps in a data science problem is, first, there is a problem definition. Then you determine how to generalize the problem. Then you determine the features. Then you build a model, and then you finally evaluate it. So let me take a very simple example. Suppose we want to say, which one the problem could be. Like, my company VMware has a product called Fusion, and many of you may have used it. It is used to run Windows on an Apple machine. So if I come up with a problem to say, out of all the 1,500 people on this call, I have a salesperson who has to target 10 people most likely to buy Fusion, then that is a business problem, right? The problem definition will be the target is who is likely to buy Fusion. The entity is the people attending this webinar. Then I have to ensure that the model that I build will be applicable to future webinars. So I'm going to collect the data here. I'm going to apply it to future webinars. Therefore, the model has to work not only for the people attending this webinar, but outside the webinar also. Then feature engineering. Now, like you can imagine, one of the most powerful feature here is going to be the type of laptop you own. Fusion is a product for Apple laptops. So if I know that you have a Windows laptop, I cannot sell to you, right? So that can be a feature in the model. Again, if you have a Mac laptop, there could be like 100 of you with a Mac laptop, or 100 of you are not likely to buy. There could be like other features, like whether you have Fusion already installed, whether you're looking to run Windows applications on your Mac, and other kinds of things, right? And then finally, we'll have to build a model. In this case, it's a classification problem, and we will have to run a problem which is like logistic regression or random forest or any of these things. And there are different parameters that we'll need to optimize. See, the same algorithm can be run by 5 people and they can get different results. The reason could be that the features you used were different. The reason could be that the algorithms you tried, the parameters were different. Like if you build a decision tree, you can build a decision tree till there are 5 observations in the leaf or 10 observations in the leaf. And finally, we have to evaluate it in the real world. So I have to take the results, I have to train the model on this webinar, apply it on the next webinar that Linus and team are running, right? So these are steps in the data science problem, and many of you would be already aware of it. The one other thing I wanted to clarify is the difference between big data and data sciences, because many of the people that I meet in daily life who want to be data scientists, they say, hey, you know what, hey Kiran, what's the course I need to take on big data? So big data is just another data source for a data scientist. So big data is information that cannot be collected or used via traditional tools. So it cannot like fit in my enterprise data warehouse. It cannot like fit on my laptop. It cannot fit, or it becomes very uneconomical to store it in the traditional form. So what big data they do is, they, instead of storing the data on one machine, they store it on multiple machines. And you know, if you want to access access something, if I want to access my assets that are stored on 100 machines, then I need a distributed file system. The distributed file system is Hadoop, and like we use SQL on a database, they'll use Hive on Hadoop. And basically what this thing does is, they distribute a job onto several machines, which is map. Processing happens on the several machines, then they aggregate the results back. So for certain activities, because there's a map and a reduced overhead, it could be slower than running it on your individual machine as well. So for a data scientist, big data is like a database. It is just another data source. So you know, to know data sciences well, you don't have to you know, if you know big data is of course great, but big data and data sciences are not the same. For a data scientist, for me, big data is just another data source, like a CSV file, like a text file, like a pipe delimited file, like an Excel file, like a ODBC connection to an Oracle or a Pivotal Green Plum or a Microsoft SQL Server database. Okay, so big data is just another data source. Then some of the things that we need to keep in mind is, more data does not mean better models. So all things being equal, more data is better, but somebody can build a better model on maybe 10,000 rows, and somebody can build on 100K rows. You know, because what the models are trying to do, the example that I gave you, which of you are likely to buy Fusion? If I have powerful features in my model, like which of you already has a Mac laptop and have information about your demographics, information about your company, and information about your past purchase history, I'm likely to do better, even if I take a subset of all of you. The other thing that also happens is, you know, models are not run real time. Models are usually built offline and they're applied in real time. Let me give you an example. In Flipkart, we built something called a user insight engine, and there one of the signals we got was that you know, we can guess the gender of a person based on his browsing history. So let's say one of you on the call actually went and went to Flipkart in the last visit, and say you saw a Hardy Boys novel, then, you know, we can guess that you're male. Okay, and then you actually go and you saw a Nancy Drew novel, then you're most likely female. So the signal that we are getting is based on your browsing history. So the model that says what your gender could be based on like what you actually browsed, you know, based on what you actually browsed, you know, is actually built offline. So the model is built and stored in an offline context, and then it is applied real time. So whenever a visitor comes, the visitor attributes are looked at, and then the model score is applied, saying he's 80% likely to be male or 70% likely to be male. And then can we customize the home page to say what to show you? So if you're male and you saw Hardy Boys last time, maybe I can show you some other books related to Hardy Boys, or maybe I can show you men's footwear or men's clothing. And if you're a woman, you know, you can probably get some kurtis or women's apparel or women's sandals, etc. So algorithms are not running real time. They are built offline and they are scored in real time, which means that there are a lot of complications in the real world as to what you can really do. So if you have a very difficult feature that will take like ages to compute, it's probably not worth having in the model. Other thing is, there are algorithms that can run on big data directly, you know. So you got Mahout and all of these things. So they do the same thing that you're doing on a sample. So just to summarize, big data is a data source. You know, for a data scientist, it's a distributed file system. And you know, for a data scientist, more data does not mean better models. A better model is going to be built by a better application of the processes that I showed you on the earlier slide. And modern algorithms are not really running real time. There's nothing like real time algorithms. There's like real time application of algorithms. And algorithms can run on big data directly, but conceptually the algorithms are still the same. So what we did so far, we talked about data sciences, and then we saw a perspective of data sciences from me, and data sciences and big data. Now, many of you will have careers in B2B, and many of you will have careers in B2C. Both of them have their own complexities. I had the good fortune of working in both B2B and B2C organizations. And this is my summary of the paradigm differences between B2C and B2B. In B2C, see the if you are B2C, the data sets will be like much larger than B2B. Like a B2B company may have like 500,000 customers, whereas a B2C company may have millions of customers. Okay, and the data set available in B2C, the influence that you can do on digital is very high. If almost all of the sales that happens on Amazon and Flipkart is going to be online. Of course, there'll be people that can place an order on a phone because they got stuck somewhere online. It's called assisted buying. But then again, most of the sales are happening online. In a B2B world, the number of customers is going to be lower than that of a B2C company, and then they're not really going to be placing their order online. Okay, and the data set in a B2C will be much bigger because if you take any visitor, he will have like 10 or 15 clicks in a visit, and everything is a row in a database, and then you have to aggregate it up, and you're going to get large amounts of data. So that's in a summary the difference. But what are some real differences in B2B? One is a longer buying cycle. So in a B2B data sciences problems, you'll find that the buying cycle is actually very high. Like if you take some of the products on Flipkart.com or Amazon.com, the average selling price is $40. Flipkart is going to be $40, same as Amazon worldwide, because large bulk of their sales in India are going to be smartphones and mobile phones. And then if you're buying a mobile phone, you're not going to go look at that mobile phone daily, check the price for 6 months or 18 months and then buy. Whereas in a B2B company like SAP, Salesforce, VMware, some of the enterprise sales that Microsoft does and HP do, IBM does, they're all having a longer time because the selling price is much higher. It's not $40. It's going to be thousands of dollars, and in some cases, hundreds of thousands of dollars. So as you can imagine, for a data scientist, you need to set aside a long period for validation. Like, you can't do validation data like you do in digital, in e-commerce, where you can say, I'll build a model to say, aggregating data up to everybody in January, see who bought in February, apply to the future. We'll probably have to take 6 or 18 months to replicate the real world. Second difference in B2B, which is a challenge, is going to be that the unit is a company and not an individual. So if I am coming to Flipkart.com to buy, so it's either me making the decision or my wife making the decision, or I and my wife together making a decision. Whereas a company has a bunch of decision makers. Somebody is an influencer, somebody is a gatekeeper, somebody is a decision maker. There are different roles of different people in decision making. So if somebody from Cisco.com comes to VMware, it's quite possible they are coming to buy some of our products. So maybe we have a sales opportunity there. It is also possible that somebody is coming to our website and checking out the career section to apply for a job at VMware, right? So that's a complexity in B2B. Then, like I said, in B2C, the sales happens online. You can do a lot of A/B multivariate tests and then figure it out. Whereas in B2B, it all happens via sales reps, and we need to work very closely with the sales rep, with the IT system to make it happen. So to have a successful career in B2B, it's very important to understand the business, be able to run these control tests with sales reps, with the development representatives, etc., and to continually tweak the models, because the products vary over time. The products have a life cycle. Somebody who buys a product 1 month after launch is not the same as the person who buys a product 2 years after launch, because somebody is an early adopter, somebody is an innovator, same as what Jeffrey Moore put in his book, Crossing the Chasm. Then there will be multiple business team goals in a business scenario. Like sales will want conversion, marketing will want sourced opportunity, partners will want their rebates. So in short, B2C and B2B have their own set of challenges. B2C, the challenges come from the humongous amount of data, and in B2B, the challenges come from that intricacies in the business world and in framing the problem. So what are some of the projects that data scientists work on in their careers in B2C and B2B? So the reason I talked about differences in B2C and B2B earlier is so that you all can relate to the slide. See, these are some of the projects that I have been involved in. A lot of the problems that you face in B2B is going to be like, which customer should I go after? So I have like 500,000 or I have like 1,000,000 customers. I want my sales reps cannot talk to, I have a team of 20 salespeople in a particular region, say Americas, for a particular product, right? I'll have many more across products. So if my 20 people have to actually go and contact customers, they can't randomly pick 20 people. They can't randomly pick 200 people, assuming each salesperson can target 10 in the next week. They can target 200 people randomly from 500,000 customers. They need to have some sort of business rules. So they will apply some business rules saying customer who bought from us in the last 1 year, more recent, more frequent, high monetary value in the past purchases, and they will target. So what we can do is, from a data sciences perspective, we actually take all the historical information about the customer, including like his past purchases with us, his firmographic characteristics like the company size, number of employees, whether they responded to our marketing campaigns, what are the different type of services they've shown interest in us, etc., and build a model. So we will go back to the salesperson and we'll say, hey, Mr. Salesperson, you have 10 people in America, 20 people in Americas, you can target 10 each. Take the top 200 from a propensity model and target. So what we did, we rank ordered all the 500,000 customers from most likely to buy to least likely to buy, and we gave it to the sales rep to call. So the sales reps can target the 200 that are most likely to buy based on mathematical understanding. Now, this is very similar to the B2C problems. Like a lot of you will work in financial services, and there the problem is always like, who is likely to default? Who should I give a loan or who should I not give a loan, right? Or what interest rate I should give? That's a similar problem. So you take all the customers, then you rank order them from most likely to default to least likely to default. So as an example, if somebody has a lot of liabilities with the bank, like he has a personal loan, he has a car loan, his wife has a loan, and then he has actually defaulted on his last credit card payment, then the bank would be wary of giving him a loan because likely to default is high. So typical problems in data sciences in B2C and B2B will be to rank order customers, and this is all falling under the classification problem, which is the 1-0 logistic regression, random forest, decision tree, those kinds of problems, right? Though some of these techniques you can use for regression as well, like random forest and decision tree can be. So that's one type of problem you have in B2C and B2C, B2B, which is ranking order customers in their likelihood to do something, like whether they're likely to buy in case of B2B, whether they're likely to default or go into bad loan in case of financial services, and online, whether they're likely to respond or not. Like if somebody is shown an ad, will he click on the ad or not click on an ad? If somebody is coming to the website, will he buy or not buy? So digital is again all about click-through. So that's how the normal problems are. Data sciences, you will also apply in many other places like marketing attribution to determine how you should allocate your marketing spend across different vehicles involved in a purchase. Like, where should you invest more, where should you invest less? That's a B2C problem. In the B2B problem on digital, it's very different from B2C. B2C will build models to say, hey, who should I show a personalized banner to? Who should I actually send an email to, which is an email rules engine. In B2B, people are not coming to the website to buy, but they're coming to the website to learn about the products. So the B2B website, you go to VMware, you go to IBM, you go to IBM's, of course, enterprise site, and you go to SAP, Salesforce. What they will do is they don't use the website to sell a lot, but rather to promote the product, because the sale is going to be closed by the salesperson offline. And the role of the website is actually to get a lead, like, to know more about you. So if Linus comes to my website and he fills a form, then I know that Linus came to our website from SpringPeople, and then I know about his characteristics, I can contact him. So digital data science is used to build a large number of propensity models, which is like which asset you're likely to consume. Are you likely to look at download an evaluation version of the product? Are you likely to download a dummies guide? Are you likely to download a white paper? All of those things. So we talked about some problems in B2B and B2C, which is like attribution, which is like propensity to buy, propensity to click, propensity to default. We also propensity to actually, your likelihood to actually download a particular asset, or where you are in the buyer's journey, what is the type of page I want to show you. So if you're like early in the buyer's journey or in the awareness phase, maybe I should show you a white paper. And if you're close to making an action, I need to get you to download the product. Similarly on the website, right? If somebody is coming to the website for the first time, maybe you want to see him to see the product details page. And then if you want in the later stage when he's ready to buy, maybe he adds to cart, so building models for all of these things. Then there are interesting problems possible on data sciences careers in pricing, like how do you optimize the list price? How do you optimize the deal price? Then, recommendation engines. So some of the things I've been involved in. So in Dell, I was involved in a project called ConfigRank, which is what is the right ordering of modules in a software configurator. Like you can configure your system at Dell, go to configure.dell.com and then say, I want so much of this CPU, this memory, this hard drive. We found the optimal ordering to show those things. Then I've also worked with a US startup to say which music label to recommend, where we use some of the factorization machines and other stuff. Then, if somebody's out of warranty customer visiting our support site, who is likely to renew? So these are some projects I've done at Dell. Some projects I did at Flipkart is like ranking customers in the likelihood to attrite. So if we know that some customer is going to become inactive, we can maybe send them, hey, we missed you email. Okay. I also designed an email rules engine that said which customers to email and what products to email them for. And whatever you see on the top, a lot of those projects are the ones that I worked at VMware, which is the digital buyer journey model, propensity to buy models, and very interesting problems as well. Like, can you determine once a customer buys a product, has he really deployed the product? Okay, which customer and which partner to match? So there have been a bunch of projects that I've been involved in. So just to summarize, from a data sciences perspective, data sciences is a study of uncertainty. There are three types of problems. The first two are supervised, which is predicting a numeric outcome and predicting a classification outcome, like predicting sales or predicting who will be in which bucket, like buyer, non-buyer, default, non-default. And the third is segmentation. We discussed that some differences between statistical approach and machine learning approach. Then we talked about data sciences and big data. The data sciences and big data are not the same. Big data is just another data source. If you ask me, I would say just another data source for me, which can store certain amounts of data like visitor click data or product log data, common use cases for big data. Then we talked about how we can have career in B2B or B2C. The exciting thing about B2C is a large amount of data and the ability to see results instantaneously, right? You can do a control test and get confidence very fast, because whenever somebody comes to digital, he's either buying or not buying, which is like a binomial distribution, which means you can get confidence very fast. In B2B, the challenges are the data will be of a lesser size, but the larger problem is a longer buying cycle, the need to actually put together controls and tests with offline entities like sales reps, and then even digital, right, where it's more about nurturing the person and not getting him to buy. E-commerce is all about getting the person to buy, whereas this is going to be more about getting people to ahead in their buyer's journey. Then what I'll talk about now is a lot of you want careers in data sciences, and you'd all want to know, like, hey, how do I be a successful data scientist? Okay, how can be a successful data scientist manager? And I will talk about these things in the coming slides, and also talk about something a lot of you would be interested in. How do I build a better model, and how can I win a data science competition? Okay, yeah. Or even if you don't win a data science competition, you want to build models that are most accurate possible, right? So for a successful career as a data scientist, I believe that you need to have two groups of skills. One is foundational and one is core. Why do I say foundational? Because that's like the foundation of the building. It has to be there to be successful. Okay. So first thing that I say is, you'll find my thoughts here a little different from what others may tell you, right? Normally people will tell you, hey, learn R, Python, take some crash course here, do some model, you become a data scientist. I don't believe that works. Firstly, it's very important to cultivate debugging skills. You need to be able to install packages, work with open source, work with new techniques, and have that never give up attitude. A debugging person is a person who's always worried about what will go wrong. He's not worried about what will be right. Because as a data scientist, to build a good model, you need to be constantly scared that I may be going wrong somewhere. I may be doing some mistake. What if what I'm doing does not work in the real world? What if what I'm building is not the best way to build something possible? So that is really a debugging thing, right? You're constantly, questioning yourself, and then you don't shy away. You don't say things like this: if I work on a Linux machine, I don't have skills in Linux, right? You're willing to learn Linux and work on a Linux machine, right? We need the debugging skill. The second set of skills is a strong data analysis skills. Like, I don't believe in the concept that somebody will prepare the data for you and you'll do the model. Look at any of the standard data mining processes. They say data preparation and feature engineering are very important. If you're just a modeler that is building a model, you don't do any data analysis, you're going to build bad models. It's very important to be comfortable pulling the data, manipulating the data, and visualizing the data. And if you're good in SQL and relational databases, excellent, because all data in the real world is relational. Like, in e-commerce, you have a visitor who comes to the site. The visitor has certain attributes, like what is the marketing channel he came from, what did he do on the last visit, what is the type of technology he's using to come to the site, is he coming from a website or a mobile app. The website has certain characteristics, like what is the web page that is being shown to you, what are the products on the web page, what is on the top navigation of the page, what is on the left navigation of the page. So everything in the world is relational, and you need strong data analysis skills. So debugging is very important, data analysis is very important, and you need to be a person who gets your hands dirty. Like, nobody got anything done in data sciences without programming. Like, so you need to program well, and you need to program in a language that supports statistical packages. For example, some of the common packages that are used in Python. One is like scikit-learn, which is used in Python. In R, there are a lot of packages hosted on cran.rproject.org. We need to know R or Python well. And the reason I say not so much of SAS is because SAS is expensive, SAS is not open source, and if you look at it, like everybody coming out of college today does not know SAS, but it's used R or Python. And people who come to industry, they will try to use the ones that they are familiar with. And R and Python being open source, there's a lot of contribution happening from people all around the world, and the capabilities that are available in R and Python are more than that of SAS by a significant by a significant margin. So I would actually say, hey, you need to use R or Python well from a programming perspective. And like I said, nothing ever got done in data sciences without programming. Learn R or Python very well. So you need to have the debugging attitude. You need to have strong data analysis skills. It's not like I'm a modeler, somebody is a database analyst. You need to know both, and you need to program. And what are some things that are core skills? One is mathematical aptitude and understanding of techniques. If you don't understand math and you want to escape math, then you're not going to be able to understand the solution or explain to one. From a business side, you need to understand what lift chart is and explain it to the business. You can't do that if you don't understand math. If you're a modeler trying to apply a certain technique, unless you know the math behind it, you're likely to make mistakes. And then next is business understanding. See, business understanding is important because it can help you translate a business problem to a data mining problem. But if you only have business understanding and you don't have debugging skills, strong data analysis skills, programming skills, you're not going to go anywhere as a data scientist. Okay, so so these are what I think are essential skills for in a career of a data scientist. So I say that there are only two types of jobs in the data sciences industry. One is to build models, like whatever you see here, which is a data scientist. Other could be to be a manager of data scientists. So there are only two types of roles available, and you'll have different titles like data scientist, senior data scientist, principal data scientist, data sciences manager, senior manager, director, VP. So these are all titles, but functionally they'll be in one of two groups. So the data sciences and the data scientist leader. The data scientist leader, right, typically could be a data scientist who grows up to be a data scientist leader, or he can be somebody from the outside, like who grew up functionally in some other group, maybe like business intelligence or analytics or master data or something, but he develops an aptitude for understanding data sciences output. So for a data scientist leader, what is very important for all of you wanting to be data scientist leaders is you need to have a strong understanding of techniques, so that you can understand and critique what a data scientist is doing. You're able to give inputs into timelines, question some assumptions, and get better models in place. Now, next is business understanding and converting a business problem to a data mining problem. Now, what happens is, it's very difficult to find a jack of all trades. There'll be some people, and some data scientists who are very good with the modeling, but have a problem converting a business problem to a data mining problem. So that's where a leader can come in and say, hey, this problem I can help you convert. But again, he needs to know what is a classification problem, what is a numeric problem, what is the data scientist trying to do, so that he can be the bridge. It's very important for a data scientist leader to have a strong review mechanism, so that the models are questioned, so that we know, like, the person who built the model built it with the right assumptions and the right kind of things. Then strong program delivery and management, eyeing the right talent, etc. So to summarize, we looked at definition of data sciences. We looked at differences of careers in data sciences between B2C and B2B. Then we also looked at what are the key skills for a data scientist or manager. So it looks like there are some questions here. Okay, so let me just okay, it's gone. So I've actually done this. Okay, then what does B2B and B2C stand for? B2B is business to business, B2C is business to consumer. So anything that sells directly to consumer is a B2C, like Flipkart.com, right? Customers are coming online and buying. So I've actually answered this. Then I've also removed the pop-up bar, which some of you were were asking. Then yeah, so this is done as well. This is done as well. Then yeah, this is done as well. Yeah, this is done. So see, for a software quality assurance other than developer, tester, manager, see see, this question, right? See, if you want to do data science quality assurance, right, the thing is, I've not come across such a role so far. So maybe as the industry achieves more scale, these roles may come up. But but if you're talking about black box testing, like taking the propensity model, then applying it, see, this is part of what the data scientist does. So if the data scientist actually just builds a model, it is not enough. He has to know it is working. So if I go to if I go to the sales head of America and say, hey, you know what, Frank, I built a great model, and when you will know how it works in 6 months, I'm not going to have a job, right? He will say, hey, what is this? You need to give me an estimate whether it will work or not work. So a data scientist does a lot of quality assurance himself. He will do internal validation to check if the model is working, and then he will also try to run a control test to ensure that it is really working in the real world. The non-technical roles in data science.
Hey, Kiran, just a minute.
Yeah.
So all the participants may not be seeing the questions, so you might want to read out the questions before answering them.
Okay, excellent.
Yeah.
So the Kiran Kumar has a question about non-technical roles in data science. So non-technical roles in data science, do exist, but that'll probably be at a leadership level, right? So if somebody, but typically data sciences is technical. So if you want to be non-technical in data science, doing things like project management, etc., there could be roles in some organizations that are pure services companies, but that's not a role that you should aspire for as a data scientist. What is the best way to start to learn about data science? This is a question from Sheetal Garg. So the best way to start learning about data science, is let me go back to this slide. Is the foundational, is to ensure that this is something you really want to do in life first, right? So because many people come to me, talk about careers in data science, I give them like a R file, a Python file, and say, can you do this for 6 hours a day, 52 weeks a year, right? 5 days a week, 52 weeks a year. Then they say no. So first is determine whether you really want to be a data scientist. Do you want to be a data scientist just because it's glamorous, or because you like debugging, you have strong data analysis skills, you like doing data analysis, you like programming, and you like mathematics? If the answer to all of these is yes, then you need to build the foundation first, which is understand how SQL works. Take up some training on SQL and relational databases. Understand it. If you have a computer science background, better, you already know it. Then learn R or Python well. There are several resources to learn R or Python well. There's a very good book that I can recommend, which is The Art of R Programming by a person called Norman Matloff. And then there is a book called Python for Data Analysis by Wes McKinney. So what I will do is, okay. So yeah, I can answer it by text separately in the chat window about these two books. There are also a large number of trainings available on Coursera. Okay. Then what about data engineer role? Does it come under data scientist? The answer is no. Data engineer role does not come under data scientist. There are data engineer roles. I had seen some of these roles in Amazon. They call it like a data engineer or something like that. So data engineer role could be the person who ensures the quality of the data is correct, who helps to create the features for a model, who actually, so suppose we say, hey, I want to build a model to say, when a visitor comes to the site, what should I show him? Can you go and create a cube that aggregates everything about the user, right? So I have answered that question. Okay, then one more question is, if big data is just another source of data, then what is the difference between data science and big data analytics? You don't need, and do I need to learn big data analytics to become a successful data scientist? Answer is no. You need to know the fundamentals of data science. You need to know the fundamentals of data science to be a good data scientist, right? Like I told you here, big data is just another data source. And if you know big data well, it does not make you a good data scientist. A big data well may mean you know how to write these queries to aggregate from multiple, aggregate on big data, but that's not going to make you a data scientist. What will make you a data scientist is the ability to actually build models and follow the process, like translating the problem to a data mining problem, doing feature engineering, running all these models, etc. Mathematical, why is mathematical skills not in foundation? So I think he's referring to this slide. So what I say is, see, if you can program well and then you can do data analysis well, you can still build good models, because the advantage with packages like R and Python is they're all object oriented, and you can actually you know, the interface to call anything is the same. So if you know how to do logistic regression, it's going to return you an object with the results. If you want to do random forest, it's going to return an object to you with the results. If you want to do neural network, it's going to return an object to you with the results. So so that's the reason I didn't put it in foundational, because you can do some data sciences models you know, without the math, but to be a really good or a great data scientist, you need to know the math well. So again, it's semantic, and somebody else may say differently. Then late career shift into data science after spending a decade in IT. This is a question from Nitesh Shetty, and I say this shift, and he wants to know if it's a recommended shift. So my answer to him is, it's never late to do something. It's always better late than never. So if you're never doing something versus doing something late and you really like it, you should do it. For whom is a shift not recommended? So somebody does not want to get hands dirty, is looking for non-technical roles in data science. If he does not want to do programming, doesn't like data analysis, this is not the right place. Then big data developer and data scientist, I already addressed it. Then the next question is from Samarth, which is, you know, he asks about programming languages like R and Python. Do Java have similar support? Yes, Java has similar support. So what you can do is, there are some open source libraries in Java which allow you to do that. Okay, so the reason why I'm referring to R and Python is, see, if you want to do data science or freelancing, you can do it in whatever you want. But when you work in a company, you have to use the tools that the company provides. And a lot of the companies today look at R and Python. So I'll actually answer a few questions only, because some questions, and answer rest of them in later. Data science and big data Hadoop I've already answered. Okay, so I've answered some 22 questions now. There are 48 more. So I will go through the remainder of the deck and answer that. Okay. So we'll now talk about how you can innovate as a data scientist. So, you know, I had the good fortune of being the Innovator of the Year and getting an award from Michael Dell in 2012, which is shown on the top right. I also had the good fortune of being a top 10 data miner on Kaggle for over a year and getting the tag of a data competitions grandmaster, having done very well in some competitions. I also have had the good fortune of some patent applications, some paper presented, and some case studies. So net message is, as a data scientist, you can innovate a lot in a company, and you can do that by trying to do that bit extra, and then, you know, doing that bit extra. Now I'll come to the part where I think many of the questions are, because I saw some questions on machine learning techniques. This is going to be last mile optimization. I see that there are around 440 participants as of now on the screen. Now let's say there are, let's say I give the same data to all of you. I give you all of you in this room, in this webinar, data set with 10,000 rows, and then I say this is the I'm trying to predict. Okay, let's say I'm trying to predict the salary of employees at Hewlett Packard, or say, okay, let's say I'm trying to predict employees of salaries at, I'm trying to predict the salary of employees at Google. So I have a data set of 5,000 employees of Google. I share the 5,000 data set with each one of you in the room. Everybody can build a model, and you can build whatever model you want. You can build a linear regression. You can build a decision tree, which is a regression tree actually. You can build a random forest. You can do gradient boosting. You can do neural network. You can do support vector machines. There are different techniques. So you can try whatever you want. and I have a price at the end of the day for the person with the best accuracy. So you see the problem, right? All of you have the same data set. You can apply whatever technique you want, and you're going to send the results to me. I'll measure your accuracy. I'm willing to bet that the accuracy of the models in this room will be like a box plot, which means there'll be a lot of people, who are around the average error, and there are some people with amazing models, some people with terrible models. So what's going to happen is majority of the people are going to build models which are like close to the maximum accuracy we can get, right? Close to, for example, if the maximum accuracy possible, if the maximum accuracy theoretically possible is 100%, but say the models can give 90, a lot of you will build models at 60%, 50% accuracy. Some of you will go to 80%. Very few will go to 85, 88. Some people will go to 89. What do you need to do to go from 88% accuracy to 89% accuracy? That is last mile optimization, right? Which is basically how you build better models. So like I said, a data scientist has to be paranoid. And if a data scientist is not paranoid, he's not a good data scientist, because if you're overconfident as a data scientist, you'll make errors. And the fun part about the data scientist generalization learning is that it's like learning any other skill, okay? And you learn it by experience. So I'll give some examples of what can go wrong. So let's say you're trying to predict the salary of employees in Google. So what I'm doing, I'm giving all of you 5,000 employee salaries at Google, and then I'm asking you to predict you build a model on this 5,000, apply it to another 1,000 which you're not seen, right? So Linus from SpringPeople can have a browser where he takes in can have a website where he allows you to download the data set, and then you can submit your recommendations, and then he will say how right you are. So in this particular case, there are a lot of things that can go wrong when all of you build models. Let's say that in the 5,000 people, I actually included Sundar Pichai's salary. So like right, last year as per public documents with Google, Sundar Pichai received a salary of close to $200 million. So if you all build linear regression models and you have the error, you try to measure accuracy as mean square error. So what is mean square error? It is actual minus predicted whole square. So if the model gets Sundar Pichai's salary wrong, so you say Sundar Pichai's salary is 0, or you say it is 1 million, then the error rate is going to be 200 into 10 power 6 minus 1 into 10 power 6 whole square, right? So and that's going to get averaged over the prediction. So the model will show very bad performance in training if you choose accuracy as a metric, because the model will try to be accurate for all the examples in the 5,000, including Mr. Sundar Pichai's salary. So in such a case, what should a data miner do? A data miner should not use mean square error. He should probably use root mean square error. So if you make error for Sundar Pichai, it's going to be like a square root of that error. Or even better, take the root mean square log error. So like I told you, right, the different accuracy metrics that you choose for a problem can impact your model in different ways. If you just use mean square error, you may get Sundar Pichai's salaries correct, but you may get all the entry-level engineer salaries in Google wrong. Your model may say that the entry-level engineer in Google gets $1 million, which is not true, and that would be wrong, right? So a lot of things can go wrong. Like the first thing is a wrong evaluation metric. Another thing is you look at all the online e-commerce portals. Look at Flipkart. Flipkart, what will happen is for things like apparel, which is like clothing, footwear, etc., they will have conversions of 5 to 6%, which means out of every 100, 5 or 6 will buy. If you take things like laptops and computers, it will be like 0.7, 0.8, I guess, which means 1 out of every 100 will buy. So if you say accuracy is your error metric in e-commerce, if you say nobody, so I have two cases where one person on my team says nobody buys. He's 99% accurate. But is it useful? But it's not useful to me, because someone is predicting that nobody is buying. So in this case, error metrics like area under curve, looking at the false positives, false negatives, precision, recall will become very important. So choosing the right error metric is very important. Then sometimes what can happen is the feature in validation may not be representative of the feature in training. So you got a list of 5,000 employees at Google, and I have to predict on another 1,000. The 5,000 that you predicted had all VP salaries. The 1,000 that you have to predict on does not have the VP salaries. It has all engineer salaries. Then the data set is not representative. So you should do some quick counts and then figure out that the data set is not representative. And if the thing you want to predict on is engineer salaries, exclude VP and director salaries from the data set. Sometimes, a lot of data miners will appreciate this. like a wrong cross validation technique. In e-commerce, if you just use random sampling, you'll be wrong, because if my goal in e-commerce is to say who will buy tomorrow. So if I take all the data up to today and then I have to say who will buy tomorrow, to simulate this in the real world, maybe I can take Jan, Feb, March, April data, train the model for all of those who bought on April, bought in April based on all of them with data up to March. Suppose I use a random sampling instead of time based, I'll be using tomorrow's data to predict today. So these are all some mistakes that can happen. Then last mile optimization, this is how to win data mining competitions. Many times when we build models, we build models using default parameters, like a decision tree, right? You'll use the default node size, which means if you use the same package, all of you will get the same results. When will you get different results? If you use different parameters, like somebody says, I want to build a decision tree with 10 observations in the leaf, somebody says with 20, somebody says with 30, then one of those is the right value. So what should be the parameters of your decision tree? So that is the hyper parameters of a model. For those that are familiar with data mining techniques, so there's been some questions on that. Like if you're building a neural network, the number of hidden nodes is something you should optimize. If you're building a regularized logistic regression, then the regularization parameter is something you should optimize. If you're building a random forest is nothing but a forest of decision trees, which means you will build different decision trees and you'll have two levels of randomness. The first level of randomness will come from building the decision tree on different observations, and the second level of randomness will come from using a subset of features in every decision tree. It's been theoretically proven in data mining that when you build a large number of weak models and then when they vote, it's called bagging, the results are better than a single strong model. So instead of building one decision tree, you will build like thousands of decision trees on different points in the sample space, like a subset of the records, a subset of the features, all of them will vote and give good results. So number of trees can be a parameter. The node size can be a parameter, etc. So first step to winning a data mining competition or last mile optimization in a company is choosing the best hyper parameters for the model. Then there are different techniques in data mining. Some of your questions are all related to that. First is linear model. So let's say I want to separate the people sitting in a room between those who have Apple laptop and those who don't. If all the people who have an Apple laptop sit in one corner of the room and all those that don't have Apple laptop sit in another corner, I can draw a line along the diagonal and say that the diagonal, the left of the diagonal is Apple buyer, the right of the diagonal is non-Apple buyer. So this is an example of a linear classifier. A linear classifier is trying to draw a line between the people who buy and don't buy, and the line is it's a straight kind of line, right? And the techniques that try to do that are logistic regression, penalized logistic regression. But sometimes, rarely will you find that everybody is sitting like that. People are probably scattered. So I have to say that the first two rows, the last two rows, and the middle two rows, okay? Then, you can use tree-based models like decision tree, the non-linear classifier. And then you can use some techniques like bagging and boosting. Bagging, I gave you an example, a number of weak classifiers voting to say what will be the right value. And the boosting is, you build models iteratively. You build a model first, you see what you got wrong, you build a second version of the model where you boost the results, like whatever was inaccurate, you gave it a higher weight so that the model tends to be closer to them. So you have linear models like logistic regression, you have non-linear models which are based of decision trees like decision tree itself, bagging and boosting techniques like random forest, gradient boosting, and extreme gradient boosting has regularization in the leaves. And you can have other types of non-linear models like a neural network. Then you can have a support vector machine. So if you want to build last mile optimization, you cannot just build a single model. You cannot say I know only two techniques, linear regression, logistic regression. You need to know a variety of techniques. You need to try a linear model, a non-linear model, a tree-based model, a Bayesian model. Try all of these models, try some 5 or 6 models, and then you have to build a model of models. A model of models is called ensemble. So I'll be sharing some example of this in the next set of slides, which is how I won a data science competition, which is the KDD Cup. So this is the KDD Cup in 2014. The challenge was to predict which projects will get funding at donorschoose.org. So donorschoose.org is an online charity that helps students via donations from individuals and businesses. So what happens is teachers in K-12 schools, they will submit projects with descriptions telling, they'll write essays saying why I should get the funding. Okay, and then we have to say what is exciting or not. So if you see there, I finished third in this competition. I was the only person with a single member team. like everybody else participated as a team, I participated as an individual. We had different data sets. One is the data set on all the essays written by the teachers. Second was like the donations, like how much donation they got, what are the terms and conditions of the donation, what are the different type of projects, like project description. Then what is the thing that the teacher requested for? Some requested for money, somebody requested for like some funding. So how did I go about doing this? So first thing is, I did some visualization. I found that in certain features, variables were missing, and the traditional practice is to try to impute them. So some of these things that you read in literature don't really work very well, like replacing with mean or median or dropping the variable, capping the variable. I introduced a new feature to indicate whenever it was missing as 1, not missing as 0, so that I understand if the variable is missing because of randomness or is it because of a pattern. Then I also saw the data prior to 2010 was not indicative of current, so I excluded that data. Then I did a bunch of feature engineering. So a lot of text mining was involved. Like I looked at the number of adjectives in every essay, the percentage of adjectives in every essay, the percentage of nouns in every essay. The percentage was capitalized, because if somebody writes in capital letters, it's probably not serious. Okay. And then see, the problem with text data is that it is very sparse. So if whatever sentence I've told on the call today, if you actually record it, convert it into text, and then put it in an Excel and say what is the number of unique words, you will probably find like like thousands of words in it, right? And you can imagine with essays written over years, the number of unique words will be in the millions. Millions, because there are many spelling mistakes as well, no? So yeah, so we have to handle this sparse. It won't fit in traditional memory if you just try to make a matrix of it, even with 32 64 gigs of RAM. So I have a personal desktop with 32 gigs of RAM, it will crash. So I need to handle the sparse data in a certain way. So to handle sparse data, there's a mechanism called a term document matrix and sparse matrices. I use that. Then what I found is that the posts that were reset, they may not have had enough time to get funding, so I gave a penalty to these posts. So what are some techniques I tried? I tried a technique called Vopal Wabbit. I tried extreme gradient boosting. I tried gradient boosting machine in R and Python. See, the R and Python implementations of gradient boosting were different. Like Python, GBM provided some additional features like subsampling. I tried undersampled random forest, a weighted random forest, and all of this was run on my home machine. And one personal learning was telling everyone at home, please don't switch off the PC by mistake, because when I'm in office, it was running. Okay, I was in Flipkart at that time. So these were the components of my winning solution. And like you see, right, just look at the scores. This is measured on area under curve. What between me and the person who finished after me, there's a difference in the second decimal place. Between the person who is above me, like the difference is 0.0003. So the difference is in the fourth decimal place. So this is called last mile optimization, building a model that is the best possible. And what actually helps this is all of these things, right? So what I'll do is there's also a link to the winners interview where I shared some tidbits. So this ends my presentation, and I will actually be taking questions after this. So just wanted to summarize what all we discussed, right? So that all of us go back learning something. So I talked about my career journey in data sciences, saying how I've grown, how I actually started off as an analyst, and then and then continue to pick on skills along the way. Then I talked about my perspective on data science, which is data science is a study of uncertainty. And where there is certainty, there is no data sciences. There are 3 types of data science problems. One is classification problem, one is prediction problem, one is segmentation problem. Classification is grouping people, prediction is predicting some numeric outcomes. These 2 are supervised, the other one is unsupervised. I talked about the difference between statistical approach and machine learning approach. I talked about if you have how data sciences and big data are different. Big data is a data source for a data scientist, and if you know big data well, it can help you in data science to the extent that you can aggregate the data better to have better features. Then we talked about data sciences careers in B2B and B2C, how B2C can have large amounts of data and you can get results very fast, which is a plus. And B2B, the minus is going to be, it's going to take you a long time to measure the results. You may have to work with offline entities because like salespeople, because they're closing the deal. And the pluses in B2B are the variety of problems in B2B is much more than B2C. Like you can build models on pricing, you can build models on partner, you can build models to say which asset to show. So B2B definitely from a breadth of problems it is wider, whereas B2C has a lot of things from a depth of problem. Then I talked about successful data scientist and data sciences manager. So just to summarize, the data scientist should actually have very good debugging skills. You need to do data analysis skills. I don't subscribe to the view that data preparation, like data engineer role and data scientist role, are different. I think they should be the same. And if you're doing only a small component, you can't see the full picture. You need to do programming well. You need to have good mathematical aptitude and business understanding. Then we talked about like what are the skills for a data scientist manager. And like I said, there are two types of core roles. One is a data scientist role, one is a data scientist manager role. Then I talked about what you need to do to build better models, what are some common pitfalls that a data scientist should avoid. And we looked into a case study of winning a data science competition from the point of view that is also important in a company, because the people who are going to grow in careers are going to be the people who build good models. So thanks everyone for this time, and now I'll go through some of the questions. Okay. So yeah, so there are some things, some questions that I will answer, and like Aaron mentioned, all of you are not able to see my screen. So yeah. So please elaborate on the different machine learning techniques. So machine learning techniques, like I said, the three types: classification, prediction, and segmentation. And there are different types of machine learning technique, like linear things, which is trying to draw a straight line, and examples of logistic regression, linear regression, regularized logistic regression. And next is like a tree-based models, which is like decision tree, creating many trees from a bagging perspective, like random forest, or boosting, like gradient boosting. Then you have like non-linear techniques like neural network, support vector machine. You have Bayesian techniques as well. Then next, how long will it take to convert to a data scientist if I'm working in business intelligence? This is from Vijay Kumar Tirumalasetti. My answer is that it is see, people have made transition from business intelligence to data scientists in my teams in the past, and I found that there's no exact time for this, right? Some people do this faster, some people do this slower, and it all depends on the person. So you have to build like 7 or 8 models to call yourself a data scientist, and you must learn all the pitfalls. So there is no exact answer to it. Depends on you. So if are you willing to commit like 1 hour a day or 8 hours a day, right? Depends on you. What about recommendation engines? See, recommendation engines, they actually recommend a product to you based on your browsing history. So let's say we are on the product detail page of flipkart.com. You're seeing a cameras page, and on the cameras page they're trying to tell you related products like SD card or maybe a bigger camera or other stuff. Recommendation engines can be called as classification problem. They fall under the classification aspect, because I'm trying to recommend to you one object out of several other objects. So I'm ranking order objects in the way to show you. So recommendation engines are an example of classification problems. So those are so that I would suggest that to look at the latest literature on that. You read up something called factorization machines. There is a very good package called libfm that gives very good results. But recommendation engines are classification problems. A priori pattern mining, see, this is you're referring, I think, to the beer and diaper example found in all data mining textbooks, where somebody went to a supermarket and saw beer and diapers together, and that was an outcome of data mining. So a priori data mining relies on three things. One is support, one is confidence, one is lift. Support is like how many times the objects were bought together. Confidence is if I bought a particular object, how can I say that the another object was bought? So a priori data mining, usually there's a chapter in some textbooks, but in the industry, the application of a priori data mining is very low. Even if you look at Amazon or Flipkart, they do not use a priori data mining to come up with recommendations. And to learn all of these things, my suggestion to you is that to pick up a very good book like Machine Learning by Tom Mitchell. So let me also just for next is Suganya Sebastian. For a DBA and passion in data mining, will data science be a good foundation? Okay, so yes, if you're a database analyst and you know SQL well, you understand inner join, left outer join, right outer join, and you can write some stored procedures, yes, data mining will be a good see, data science is not a foundation for DBA work, but DBA work will be a good foundation for data science. Okay. Then is Apache Spark. Next is anonymous attendee. I don't know who you are, but your question is like, is Apache Spark knowledge enough for machine learning? Answer is no. If you know how to use a tool, you're not going to be a good data scientist. You need to understand how the different techniques work. You need to understand how to convert a business problem to a data mining problem, how to come up with features, what are the different modeling techniques, and how you can use them. SQL is DML and DDL are enough. Okay, this is a question from Deepak Konur. So my answer is, it's just if you see, you need to, when I say you know SQL well, you know how to create a data, create tables. You can create tables with relationships between them. You can understand the relationship between the tables. You can actually write stored procedures. You understand how to join two tables, etc. So there's nothing like, you see, there are two ways to look at it, right? Can I know the bare minimum of everything and become a good data scientist? Answer is no. You need to know, go into things in further depth. Then next question is from Praveen Jana. So I'll answer this by text. I'll tell you why. The reason is I have recommended some books. I want to just be it in public domain. So Machine Learning by Tom Mitchell is what I recommend for machine learning. Then R Programming, the book by Norman Matloff, because some of you have said how to learn R or Python. Python programming, I would recommend the book by Wes McKinney. Okay, here's a book called Python for Data Analysis. So if you're picking up one tool today, you don't know any of the tools, pick up Python is what I would say. In-depth math knowledge is like a core skill is desired, and then to know all the internals of gradient descent, Gaussian models, etc. See, what happens is you need to definitely know what is gradient descent, because all the machine learning techniques are using that. There's a very good gradient lesson class by Andrew Ng on Coursera that you can take. Okay, class on Coursera by Andrew Ng. Okay, so I have answered your question. This one question I've actually answered publicly because a lot of you have asked for this thing. Next is, what is the difference between machine learning and data science? There is no difference. They are the same. People are using different techniques to call all of these things. And then again, some people can say there is a difference and this is a semantic difference. For all practical purposes, there is no difference. Next is, what is a normal project life cycle and duration of a data science project? See, a data science project from a life cycle perspective will involve talking to the stakeholders, understanding the business problem, trying to see what are the actions that the business person can take, and then having a target variable suited to that. Right? First is always the business problem to data mining problem. Next is going to be the feature engineering, and then it's going to be about building different models, then putting it into production. So if you just take the modeling portion of it, which is from a data, then the modeling portion will probably be like a week or a couple of weeks. Again, it depends on the skill of the data miner. Has he solved a similar problem in the past? So if you already built a model for a particular product, I want to build for another product, it is like I can reuse a lot of the code. What is the ability to do reusability as well? Right? So if you take the entire project from the business problem to a data mining problem, that can take like 2 to 3 weeks. Again, this is just indicative, and finally to get it implemented. To get it implemented and measure the results can take a long time. Our tool is freeware. Answer is yes. The question was from Revanappa Shivagi. Then is there any role called data engineer? Is it come under data scientist? I already told you that there is a role called data engineer, and it depends on the company. Some companies like Amazon have it. My philosophy is that a data scientist should also be able to do data preparation. Is it mandated to have hands-on with data scientist role to become a data science manager? Answer is no. But to be a good data science manager, you need to know data sciences, right? If you're managing something, see, what is management? Management is managing something. If you don't know anything about what you're managing, you're unlikely to be a good manager, but some companies may give you that role. What is the career path for SAP BW consultants to become better data scientists? There is no specific career path, so I can't tell that if you're a SAP BW consultant, you have to read these kind of books. You have to read the books that everybody else is reading, like the R, the Python, etc. And like let me go back. Right, looks like all the questions, a lot of the questions are for the career. So let me just have this thing open. Okay. Please share any good portals or books for machine learning. I've already shared that. So by text. Can we learn Python language only to become a data scientist? Yes. Do I need to have hands-on experience in Python? Answer is also yes. Why R and Python? Why not Ruby or Node.js? Okay, this is a good question. Like, you need some libraries also, no? So if you R and Python have access to all the machine learning libraries, if you want to learn logistic regression, you're not going to write the logistic regression function. You are going to actually call some function in a library. So that's why I recommend R and Python. Then can you give, please give more data on the model to build how it works? I'm going to answer this through text. The reason is so that all of you know repository where data sets are available. The USA repository, the University of California at Irvine has several data sets for you to try machine learning. Okay, so I've already answered this question. Except Python, can you write it in Perl or shell scripting? You can do data preparation maybe in Perl and all that, but you need a statistical package. Can data science be integrated with SAP? Yes, I'm sure SAP has already provided some functionality for this. Just by learning stuff, will it make a data scientist, or will it come by experience? Answer is by learning and experience. Is Perl support or only Perl? I don't know of any data mining package that it supports, so it's only Python. Then some questions I've already answered, so I won't take them up. Segmentation can be considered as unsupervised, right? That's what I said. So segmentation is unsupervised. However, certain segmentation can also be supervised. So if I already know which segments they are and I try to build a model. Next question is, somebody has 12 years experience. There's no right answer to this, right? To when to start data mining, it depends on your personal interest. So somebody, there's never a late skill. Is there a late skill to learn how to drive a plane? The answer is no. Similarly for a data scientist. Any curriculum available? There are a lot of things I've already shared. Difference between data science and data analytics. See, data analytics may not involve building models using statistical packages. So data analytics may answer a question like, what is the right shipping threshold at Flipkart? So should we give free shipping to anybody who buys something more than 500 rupees, or to somebody who buys more than 800 rupees or more than 300 rupees? The moment you increase your shipping threshold, your cart size will increase, because you get shipping, free shipping, people add more things to the cart. But at the same time, your conversion will fall. Some people will say free shipping at Flipkart is 500 rupees, whereas at Amazon is 250. Let me go to Amazon, right? So these kinds of problems are data analytics. Data science is building all these different models. Then Venugopal Daliparthi, I like data analysis, spend most of my career in PMO kind of roles. Can I switch to a data scientist manager of role? Yes, you need to complete some courses on Coursera, then you can. And then, so the answer is definitely yes. There are PGDM programs like IITs, triple IITs and IIMs. Do they give a good foundation for data science? See, there are some programs I'm aware of, like the IIM Bangalore program, which is a PGP program on business analytics done part-time. I think that is a good course. Yes, they give good foundation. See, a teacher can only take you to the water, but you have to drink that water, no? Yeah, okay. Then Sheetal Garg, how to build debugging skills for data science. And see, debugging skills is something which is a personality trait. Like, you never give up, you try different things, you're paranoid about what you do. So there's no training for that. There are trainings on R programming, Python, etc. So career, see, a lot of you have questions on like Vivek Muruganantham has, which is like how to make a career as data scientist from other roles. See, you have to build all these skills, and there is no specific career path like QA manager to data scientist. You can do that. You can even do agriculture and do data sciences later, provided you pick up these skills. A lot of questions on like years of experience. I'm skipping them because they are similar. Level of mathematics, the more the better. There's no sweet spot to that. Then some questions are all very similar. So let me just pause for 2 minutes and go through the questions. Some I have already answered. So yeah. Sandesh question, recommendation systems are classification problems. Okay, Rakesh Kumar has a question. If the outcome of the model is uncertain, how do I know whether a model is right and what outcome is the best? So let me take an example to predict which of the people in the room will have ice cream. So I may predict that most likely 25 people of you will have ice cream, and somebody else predicted most likely some other 25 will have ice cream. So we can compare the results of who actually had ice cream and then compare the results. So the outcome is uncertain, but you can compare against actual and say how accurate you are. So some questions like data science, this is all answered. Advanced Excel skills, see, you need to know R or Python. You can't do data mining in Excel. You can maybe do some data mining in Excel, but definitely not in a form that is useful in the industry. Then machine learning and
Kiran, you might want to be a little more selective with your questions so that there are a lot of questions here.
Yeah, I've answered 67. I see 132 more. So
Yeah.
let me just
So I'm
go
just saying, you can be selective with your questions, choosing the
yeah.
questions that you want to answer.
Okay, cool.
Yeah.
So I will answer some questions, some use cases of in IT services, right? This is from Varsha Patnaik. So, uh, in IT services, right, you are providing a service to your customers. You're going to build models on what your customers ask you to build. So typically, it will encompass the data sciences space, because some of your customers might want to know in financial services who will default, retail industry who will buy, and what kind of promo you should do, etc. Then Anjali has a question: how to build a good model to get a better outcome. So it is there here, which is you need to tune your hyperparameters, build variety of models, and do ensembles. So what is the automation effect for data scientists, right? So this is a very interesting question. So I think I should answer this. This is from Shrikant Muktala. See, automation is can happen to a data scientist job, some of the things as well. Like you have heard of companies like Data Robot that are trying to automate data mining predictions. See, this is something common in every industry. Things will get automated, and what economics has shown is that every time a job is automated, there are one or two better job opportunities that come up. So automation is definitely possible. The data scientists are also automating several jobs. Then see, a lot of questions are semantics, like data scientists and decision scientists, they're all what companies are saying. Then some people have asked similar questions. And what is the demand and salary package for data science? Okay, so see, this varies by company, but typically data scientists in a company will typically it's all demand and supply, right? So whenever the demand is less and the supply is more, then the salaries will drop, like we have seen in IT services, the software engineer entry salaries. So in data science they'll typically be higher, and rather than me answering the question, you can go to glassdoor.com and check for yourself. Okay, then so a lot of people seem to want to know about salaries, but for that go to glassdoor.com. Then is it necessary, Deepthi Singh, is it necessary to have some certifications to switch profile to data scientist in corporate world? See, all companies are going to test you on what you can do. So having a certification or a degree does not mean anything. However, having a good certification can be useful, because a lot of people may say, I know data sciences. Somebody may come and say, hey, you know what, Kiran, I've actually completed this course on Coursera by Andrew Ng. I've actually got this John Hopkins University certification of data sciences, right? So in such a case, it can be an indicator of seriousness, because wanting to become a data scientist versus somebody who has a certification, I would pick the one with a certification. Then do we need to learn statistics to become a data scientist? I've already answered this actually initially in my presentation. I think I can take two more questions and then I'll hand it over to Aaron. Then a lot of questions are there on SAS. So my answer is that better to have strong skills in R and Python. For example, just FYI, I'm SAS certified base programmer. I'm a SAS certified enterprise miner. I got all these certifications in 2009-10. However, SAS is not an absolute. SAS, between SAS and R, I would pick R any day. Best book. I'll take one more question. So let me choose a good question. How can we get into data science? This is a question from Vijay Prabha Brahma. Her question is, can we get into data science along with our day-to-day job? Okay, if daily job is not related to data science. Answer is yes. You can, you can pick up a book and learn R or Python programming very well. You can do a course on Coursera, like the John Hopkins course or Andrew Ng course. You can download data sets from the UCI repository, build models. You can go to Kaggle.com and participate in some data mining competitions. You can do a bunch of these things. So looks like I answered 73 questions. There are many other questions as well. I'll go through them, and if there's any interesting question, I can actually answer them as well. But I think that was it from my side. So let me just get the thank you slide on in multiple languages. Okay, so over to you, Aaron. Thanks everyone. It was great interacting with you.